Okay.
You're online? Yes. So let us welcome Christopher Hughes, a longtime contributor to the algebra part of MATLAB, who is now going to talk about the word problem in one-relator groups. So thank you, Chris.
Okay, thank you. Okay, yes, word problem in one-related group. So, what is the...
Full screen, not sharing your screen.
I'm not sharing the screen.
You're sharing, but you need to go full screen in your PDF software.
I am full screen in my PDF.
It got smaller when you full screened it.
Okay. Then I just...
Now it's bigger. Now it's as big as we've seen.
Is that big?
Now it's even bigger. Take it. That'll do. Take that.
Okay. So what does this mean? What's the problem? So I'm solving. So writing an algorithm to prove problems like this, where you just have one equality of group expressions, and you want to prove a different equality of group expressions. So here, a couple of examples. So it's an implementation of an algorithm by Magnus. He wrote it in 1932, and it's a decision procedure. So you know, if you have more than one relations, then this is actually undecidable. But with one relation, there is a decision procedure for this. Next slide. Okay, so I wrote a tactic that did this. I wrote this tactic, and Kevin Buzzard posted about this on Twitter, and it turns out this wasn't necessarily a particularly good approach to the best approach to this algorithm. Wasn't the best approach to writing this tactic. In fact, there are algorithms that do more than one relation, but they're just not decision algorithms. Are only semi-decision algorithms. So, and they're probably more appropriate for useful. They'll be more useful as a lean tactic. What's the difference between so semi-decision means that they terminate when there is an equality, when the equality is true, they terminate. But if you feed it something that's false, then they might not terminate. And decision procedures will always terminate whether the goal is provable or not. So I'll just so as an example. So really, we don't need a decision procedure, because if I take an example of one of these propositions, like the first one is a proposition that I might want to prove in lean. That's the sort of thing that might be typical. The second one, which is the negation of the first proposition, you rarely want to prove that that two elements are not equal in some group. You want to prove that they are equal in all groups. So really, we only need a semi-decision procedure, and semi-decision procedures are a lot easier to find, because it's actually quite difficult to sort of prove the existence of a group, but this will just be a sequence of rewrites. So the semi-decision procedures that people mentioned on Twitter, one of them was the Knuth-Bendix algorithm. This is quite well known. And Kyle Miller from Berkeley commented that he had another, on his website, he had another procedure that solved this for more than one relation. So I'll just explain what, so I actually implemented something very similar to what Kyle Miller did, and but I'll just talk about what Knuth-Bendix is. Given a set of relations, the Knuth-Bendix algorithm finds a confluent rewriting system for those relations. So here's some equalities, and it's really an algorithm for monoids. So, and it just Knuth-Bendix will compute a bunch of simplification lemmas, and if you simplify with these lemmas, you'll put a word into a normal form, and this will, if there is a proof, this will find the proof. It's a decision procedure. For this particular group, it computes a decision procedure. The trouble with it is usually you can't find a finite set of rewriting rules that will actually normalize the expressions, but you can still have a sort of semi-decision procedure where you just keep on applying. You apply all the rules you have, and if you can't apply any more rules, you just search for more rules. You can always compute more of these simplification rules. So yeah, and that will eventually you'll find a proof if there is one, but you won't know if you can simplify it any further, because this is an infinite set of simplification rules, so you don't know whether there's a simplification rule that applies. So now I'll go on to sort of Carl Miller's method. I actually wrote a slight adaptation of it because I mean, Carl's website couldn't prove A inverse equals 1 implies B equals 1. So there are a few problems, but so I've made a few changes. So what do we do? So here's an example. We've got of a relation AB squared equals 1, and we're trying to prove that A and B commute, let's suppose. So first of all, just rearrange this equation to so you have 1 on the right hand side. And then using this relation, we can write down a whole bunch of different equalities. These equalities all follow from this relation, just by sort of rotating it and putting different things on the left hand side and right hand side. So we've got this set of equations. And so we could rewrite this word using these equations, and we actually generate the set of all words that you can reach from my starting word with just one application of one of those equations. And you reduce them, so you apply you cancel inverses, and you add each word to a set of nodes. So here's an example. So we might swap that A, and we'll add this the word B to the minus 2, A to the minus 2, B to the minus 1 to the set S of nodes, and then you just keep, and then you find the shortest word in your set of nodes, and you sort of repeat the process at that shortest node. So and you keep doing this, and so the shortest word might not be one of the words you just added. It might be a word you added a long time ago, so it does a bit of backtracking as well, effectively. So it's quite straightforward algorithm. I'm sure is a sort of well-known path-finding algorithm, really, that's applied to groups. And yeah, so when I say the shortest word, we reduced words at each stage. So for example, if I end up with this word, well, this is as a conjugate of A inverse. So if this long word is 1, if and only if A inverse is equal to 1. So you just sort of, if you can make a word shorter by conjugating it, then I do that, basically. So how does the tactic work? So first of all, just all hypotheses and the goal, put 1 on the right hand side, and you sort of compute a bunch of words in the free group. So you convert all your assumptions to we have some efficient representation of the free group when you compute what our relations are as sort of efficient as elements of the free group.
All right, Chris, when you said the tactic, this is the decision procedure for...
This is like the lean tactic. So I've described sort of how the sort of decision procedure works, but I have to actually write a proof as well. So yeah. And this is for this is for the path searching algorithm. This is not the Magnus's method.
That's
Yeah, then we search for the path on an efficient representation of the free group. So we don't search for the path like in the tactics state or anything like that. And we use this efficient representation. So the actual hard work is done completely outside of the tactic framework. And I think that makes quite a big difference to the performance. If you're sort of, using the group tactic to check if two group expressions are the same, that's a lot slower than just multiplying the sufficient representation of the free group. And maybe that changes in Lean 4, I don't know, maybe. But you have to keep enough information to, keep track of all the words that you go past, and then you can reconstruct a lean proof from this path that you've traced. So, sort of, what does the proof look like? So, given an on world, just to be clear, here equality. These are words in the free group. Equality means sort of they're literally the same group expression, and I use this squiggly line to mean it's an equality that follows from that can be proven from the relations. So that means that, so R is not the word one, but it can be proven to be equals to one. So at every stage you have an old word and a new. So if my old word is one, then, and I have all of this information, two words that multiply together to make my old word, a relation, and some words A and B, then I basically sort of insert the relation in somewhere in my old word. Maybe I conjugate it, and maybe I conjugate the whole word, and then I know that this new word must also be equal to one. So the actual lean proof is just sort of more or less just sort of repeatedly applying this, constructing a term of this inductive proposition, and you just repeatedly apply this. And then you've got some equalities to prove, and you can use the simplifier to prove these sort of hypotheses, but you can actually even just use REFL, because these are equalities of elements of the free group. They're not equality of elements of my sort of group that's in my tactic state. They are just equalities of words. So you can just use reflexivity to prove this if you want. And that's not too, that's a fairly efficient way of doing it. So I'll just go compare the three methods. So Magnus's method is the one I did first. It's a decision procedure, but it only does one relation. I did implement this in Lean, but it was, and this is a very, very complicated method. It's much more complicated than this path searching method. So yeah, probably it was months of work to implement, whereas this was sort of around about a week. And that's kind of not surprising, because it is sort of a lot harder to prove things aren't equal than are equal. So it's not surprising it's a more advanced algorithm. And I haven't written Knuth Bendix, but there are, Gap and Magma have an implementation of this, but it's not quite set up, and it's unverified. It doesn't want to prove in it. It's not set up as the sort of quite the right way that you want for a lean tactic. It's not it just sort of computes the simplification rules first and then attempts to rewrite, rather than sort of doing them both at the same time, like the like you'd want for a semi-decision procedure. Okay, let's have a demonstration. Okay. So how do I do this? So Zoom. Zoom. I want to share.
You're trying to share a different window, Chris?
Yeah, but I can't actually be.
Better to stop sharing the current one.
Okay. Hang on. Let's stop share. Share screen. I don't see VS Code in this.
Have you got more than one window, more than one monitor?
Yeah, even
No,
more than
I'm
one
on it.
workspace can confuse Zoom. You should put the VS Code window in the same workspace as the Zoom one.
I don't know what a workspace is. I'll just.
Is it full screen? Sometimes when things are full screen, it can confuse Zoom. Don't know.
How do I? Oh dear. Share screen. Oh, there we go. Right, everyone can see.
Yes. Right.
Everyone can see. Yes. Okay, so I'll just go to my presentation. Let's just restart these. Going on.
Maybe restart the server.
Yeah, I'll restart it again. There we go. Oh no. Okay. Maybe this isn't going to work. I don't know.
Tense.
Oh dear. Really? I'll just comment out that one. Okay. Okay, so I've got to try. Okay. Okay, so it's working now. So as you can see, it here's some of the things it can prove. And how long does it take? So that one took a long time because that was quite a hard problem. This one took, basically, took quite a long time. So what are the limitations of this procedure? Well, so it could manage this one, but if I feed it the extra hypothesis that A times B equals C, this ruins this basically makes it take much longer because it's trying to make everything shorter, but it applies this lemma, but really we shouldn't be applying that rewrite rule at all. So that's one way in which it's stupider than a human. It can't do this test 3C, so this is quite a tough. These ones are really quite sort of difficult because you've got to actually make it a lot longer to prove this. So the reason this is true is because a to the 5 times b times a to the minus 5 is equal to b to the power 32, and that of course commutes with b. But in order to yeah, you've got to make your word a lot longer before you actually make it short as that. So this is quite a hard problem. But then this isn't very typical of a sort of a lean tactic state, because it's got a huge number. It's got five.
There's also a C that's not. What's the C in there?
Oh yeah, sorry, that was it's not even true. So that's another reason why it's difficult to prove. But anyway, yeah. But so
what happens if you run the tactic on it? It just
I don't want to crash my computer.
Oh, I see. Okay.
Well, yeah, it will just take too long. But it's got to do sort of a lot of rewrites to make it longer. But then this isn't something I'm claiming that this doesn't really matter, because I shouldn't be proving this in lean. What I should be doing is proving the general theorem, which is that a to the n times b is b to the 2 to the n times a to the n, and that will help me prove this theorem. And actually, it does this one quite well. So you do induction, and if I just feed it the hypotheses that b and b to the 2 to the n commute, and that a to the n and a commute, and this could be done automatically at some point, then actually it just proves this goal very easily. And you can see the tree size there. It's searched 141 different words, and it did it in 5 steps. And if I just look at the profile, so most of the time I think will be spent so I only spent 30 milliseconds actually sort of finding that path, and the rest of the time was spent just on simplification and stuff like that. The actual solution only took 30 milliseconds. So the other things it doesn't do very well is I'll just write another test. So if I do So it will handle like commutativity assumptions in quite a dumb way. So maybe that could be improved as well. But yeah, I've just crashed my computer again. But I was really surprised by this, by how effective just something that isn't particularly sophisticated works on these lean goals. I'll switch back to my slides now. How do I do that? Zoom, stop share screen.
So what happens when it's not provable?
It just doesn't terminate, basically. Occasionally it terminates. In rare edge cases, it terminates on things that aren't provable, but usually it just doesn't terminate. Okay, now I can't share the I'll just hang on. Desktop. Sorry, Adobe Reader's disappeared from Zoom now, so I don't really have to. Okay, so what have I learned? That brute forcing methods work quite well when there's a small number of hypotheses and the proof that is not going to be very long, and that often we don't want a decision procedure, we only need a semi-decision procedure. And actually, semi-decision procedures are a lot easier to write than decision procedures. So I think this first point is quite an important point. So there are other problems where maybe just you can just solve them by brute force. And I think category theory. How do I go on to the next slide? Category theory is one of them. So here's a category theory lemma that I got from NLab, and this is the sort of thing where if there is a proof, without knowing what the proof is, you can guess that it's probably not going to be a very long proof, and it sort of follows directly from the axioms of a category, more or less. There's no sort of hard theorems you have to invoke. It will just follow straight from the definitions. So this is the sort of thing where maybe just a brute force algorithm would be quite useful. And I think that's the end. Any questions?
Did you PR it?
No, I only finished writing it 2 days ago, so it's not commented or anything.
So,
Is
yeah,
there
so
anything you could do to prevent it from crashing your computer if it doesn't work? Not
yeah,
working fine, but crashing the computer is a bit annoying.
Yes, that is a bit problematic. I don't really understand.
I've seen earlier versions which definitely did not crash its computer. Just to, just to be clear.
Yeah, it doesn't usually do that, but I don't know. Yeah, that it doesn't even work with the latest MATLAB for some reason as well. But
so, just to check my understanding of the basic definition there. So, for example, maybe checking that a prime is a sum of two even numbers is a sorry, not sum of two even numbers. The goal bar.
Sum of two primes.
Yeah. That's the other. Yeah, that's what I meant. Is there's a semi-decision procedure for that, for example. Yeah.
No, if it's a particular even number, then it's. Then
given. Yeah.
So. No, that's a decidable problem.
No, that's a decidable. Yeah.
The sort of the converse of the Goldbach conjecture is a semi-decision procedure, because you can just look for a counterexample.
Yes.
Yeah.
If it's checking whether one exists, a counterexample exists, there is an algorithm that terminates if it does exist.
Also, general proof search is a you can just search all proofs that exist, right?
But I mean, what's surprising to me is that sort of how practical that is. In it doesn't sounds like a disastrous idea, but maybe it's not. And, as long as you sort of enumerate your proofs in a sensible order, in a clever order, then that actually works.
Do you know whether the existence of the decision procedure for one-relator groups means that your semi-decision procedure is also a decision procedure? In the sense that, can you tell after running the search for long enough that it's not possible for you to find, like at some point you can say, oh, this is actually a failing search, like I should have found it by now?
Oh, yes, I think so. Yes, actually. I mean, it's a very long time. It will be like, if it's length n, it will be like 2 to the 2 to the 2 to the 2, like n times. But yeah, because there's sort of there is a sort of bound on the number of rewrites you can do, and that's how. I mean, that's yeah.
Can't you combine such a semi-decision procedure with an approach like in a slim check, I mean, a counterexample generator? So I mean, you could tell if I'm not done after 5 seconds, and maybe I switch to looking for counterexamples.
I mean, it's quite difficult if your counterexample, and that's why. I mean, can't.
You could pick a random group and then see whether your thing works in a random group.
Yeah.
Except that in a random group, you cannot decide whether the equality that you want to prove is true because the undecidability.
You need a random group where the relations hold, right? That's hard.
Yeah, you just pick a random group, see if your relations hold, and see if the other one doesn't, right?
Add a bunch of random relations.
Yeah, but the trouble with that is that search actually won't terminate all the time. Provably will not terminate.
The moment you start adding relations is the moment that you stop understanding equality.
Right? Okay.
You seem quite down on the fact that these semi-decision procedures exist, but I guess there must be some theoretical consequences of the fact you proved a decision procedure exists, right? Like, have you explored those at all?
Theoretical. What sort of theoretical consequences?
I think there are group theorists, you know, they.
Is it the fact that
no, the existence of a decision procedure for a certain group actually give you some group theoretic properties of those groups?
Yeah, I don't really know much about that. I know that there's a thing called a Dane function for a group. So if you have a group presentation, it's sort of more or less sort of for a word of length. Then what's the worst case number of rewrites I'm going to have to do to prove that that word's equal to 1? So if the group has a decidable decision procedure, then the Dane function is a recursive function. But that's it. I don't know if that's. And yeah, so that maybe that's an interesting group theoretic category. I mean, recursive doesn't narrow it down very much, does?
Maybe we can ask also the fashionable question. I mean, while you were implementing this, did you notice anything that would be much easier or faster in Lane 4?
I think I was using an RB map quite a lot, so I think that RB maps are supposed to be fast in Lane 4. I don't know, because supposedly Lean's quite bad if you've got sort of some large like array or something like this, and you just keep on sort of changing elements of the array. You've got one array that you're keeping track of throughout the whole computation, and that's sort of I'm keeping track of some big tree the whole time, and so maybe that will be improved. But I'm not sure, because at the moment I think it sort of deletes the whole tree and then computes the tree every time you change it. But I don't really know. I don't really know if that's going to be better. But I know it's a lot slower than the JavaScript version in Lean 3. So, but whether that's due to my crummy programming skills or Lean 3, I don't know.
I mean, you're also keeping tracks of proof. I guess the other implementation is not keeping tracks of proof.
No, Kyle's version. So Kyle's got a sort of a slightly different version of this in his website, but he actually writes a proof in LaTeX, so you can.
Oh.
Okay, so maybe one more question from my side. So, I mean, I was very surprised that apparently the best approach that we have here to solve this word problem in groups is essentially running a generic theorem prover on it. There doesn't seem to be much of like knowledge about groups in there. So, I mean,
I think Newth Bendix might actually be better than this algorithm, but yeah, I think if it's there might be sort of in particular groups there's better things, but a really general one you have to
Right. So my question is more: have you actually looked at trying automated theorem provers? I mean, how well they do on those problems?
No, I haven't done that.
Okay.
Yeah.
Wasn't somebody writing some hammer for lean at some point?
Yes. That was kind of my thought. I mean, just running a super on this and see like the difference. Or even just writing it to a text file and running proof of 9 on it and looking, I mean, like, how is the performance difference?
I think there is a sort of a bit of intelligence. It's not sort of advanced group theory, but you are, you know, you're effectively inserting all the rotations of these relations. So, I guess just knowing that you can conjugate all these relations is something that
even the information that your operation is associative is built into your data structures. I mean, maybe this is already also.
Yes, yeah, that's important. That's very important.
Also, general purpose theorem provers also, they see a lot of associative operations, so they build something in for this as well. I don't know.
Yeah, so just a quick note. So there is some work on kind of rewriting modular associativity commutativity in the Coq world. So it might be implementable in Lean. I can at least link a paper on that in the chat.
Oh, you linked a paper. Okay, thank you for that.
We have some of that in Lean as well. I don't know how the Coq associativity and commutativity system works, but in Lean, the congruent closure system has some support for associativity and commutativity, so that there's AC REFL that does reflexivity modulo associativity and commutativity. So there is some support for that.